Great.
Okay, good morning. What I'm going to do today is I'm going to wrap up the topics of chapter 11. There's a couple that I want to cover. One is a relatively lengthy problem, so I want to show you some work on that. And so it's just a couple of different problems we're going to look at today. Okay, so let me go ahead and show you the first type of problem. Close this up. Okay, so here we go. Let me share this. Okay, so this type of problem, there's several iterations of it. These are diagrammatic. They give you little pictures here, and you need to kind of interpret what's happening physically. So this is really, we're talking about physical phenomena right now, not really chemical. And there are 4 different quantities that are studied in these problems. One is density. The second is what's called viscosity. The third one is vapor pressure. And the fourth one is surface tension. So density, surface tension, vapor pressure, viscosity, those are all examples of what we call physical properties. They're not a chemical phenomenon. We're not talking about atoms and molecules changing or transforming. We're just looking at the physical properties of substances. So this first one here, what they do is they tell you, if you read it carefully, 35.0 microliter drops of different liquids, that's a pretty small volume, are put on the same surface. Half an hour later, the drops look like this, okay? So if you take a look at the first one, you can see it's a drop, right? It's like a drop of water, and it's rounded like you would expect if it were on a surface. And the second one is true also. But if you look at them, the liquid Y is smaller than liquid X after a half hour, right? So they put the same amount at the beginning, but now after liquid Y is smaller. So why would it be smaller? Well, I guess one possibility would be that it's getting absorbed by the surface. So I guess that's one possibility. But look here, it says, you may assume that neither liquid interacts strongly with the surface. So they're telling you that's not an issue. So really what's happening is liquid Y is evaporating, right? It's evaporating. You know that if you put some water on the floor over time, some of it will evaporate off into the air, right? And that's what's happening. So liquid Y is evaporating more rapidly than liquid X is, right? And they're probably both evaporating, but one is evaporating more rapidly. So the question then is, what's different about these two? Well, they're evaporating differently. Your answer should be a 1 or 2 word name of a physical property. And the ones that are in this section are density, viscosity, vapor pressure, and surface tension. Those are all 1 or 2 words. So for this one, if you recall our discussion from the previous lecture, we talked about, vapor pressure and evaporation and boiling point and heat of vaporization. That's what's happening here. This one's evaporating more quickly. So it's really an issue of vapor pressure. The higher the vapor pressure of something is, the more rapidly it evaporates at a given temperature. So if this one has a higher vapor pressure, it will evaporate more quickly than this one that maybe has a lower vapor pressure. So the answer here is just vapor pressure, right? Those are the 4 categories. Now, in theory, you could say heat of vaporization, but the 4 physical, I guess the heat of vaporization is also a physical property. Is that a physical property? I guess it is as well. But the 4 physical properties that you're going to go through are density, surface tension, vapor pressure, and viscosity. So this would be vapor pressure. Okay, let's take a look at a second one. Oh, this is interesting. I haven't seen this one before. the same small insect is seen walking on the surface of two different liquids, right? So there's two different liquids. Now look what happens. I don't know if you've seen these things. They're really cool, right? These little water walkers. See how the insect here, it looks like a spider, but it's got 6 legs. This one over here, see the indentations on the surface of that liquid? Now look at the indentations over here. Those indentations are larger, right? So that same insect is pushing down the liquid more here. So that's not an issue of evaporating. It's not evaporating. Now you might think maybe it has something to do with density. So it could be related to density in a sense, but this is an example of what we call surface tension. So surface tension is a resistance of the surface of a liquid to being displaced or pushed away. So what's happening here is in liquid Y, the liquid has a lower surface tension. So the insect with the same weight is able to push more of that liquid away to depress it. It's actually surface tension is a force. So what happens is you push down on it, it pushes back up. The greater the surface tension, the more tension, the more it will push up. So it takes more pressure, more force to push it away. So this is an issue of surface tension. Okay. Now take a look at this one. See, it says here there's 43.0 microliter drops of two different liquids, and they're put on the same surface. Okay, so same surface, and again, assume that neither liquid interacts strongly with the surface. So look what happens here. See how this one's more spread out, and this one is more, less spread out or more contained. Okay, so it's a little difficult, but to me, it looks like they have the same amount of material. It's not like this one has evaporated. It's just spread out more, right? So what does that mean if it's spread out more? Well, it's not evaporation. That's not the issue. It's not really viscosity, because viscosity, well, actually think about it. Viscosity is a resistance to flow. And then surface tension is, essentially how strong the surface is. Well, to me, it looks like this surface here is a little weaker than this one here, right? Like the liquid, gravity is pushing down, right? Or pulling, I should say. Gravity is pulling down on these liquids. So gravity is pulling this one further than it's pulling this one. So this one looks like it has a higher surface tension. The resistance to being pushed around or pulled around is greater in this one here. So it looks like another surface tension. Here's another one. I'll do two identicals. Oh, wow. There we go. Let's take a look at this one. This one's a little different. 271 milliliters of two different liquids are poured into uncovered identical beakers and let stand for 10 minutes. So there's liquid X. So after 10 minutes, this is what happens to X. After 10 minutes, this is what happens to Y. Okay. So if you look at it, this one started off with a lot of it. It's uncovered. So, the airflow can happen. It's gone down, right? This one's gone down by quite a bit. This one hasn't gone down at all. Okay, so this one's evaporating much more rapidly than the liquid Y is. So X evaporates more. So evaporation, that's the issue of vapor pressure again. So this one has a higher vapor pressure. This one has a lower vapor pressure. Okay. Here's another one. Photographs have taken of falling drops of two different liquids. Wind for liquid A, wind for liquid B. So they're dropping, these are drops. So look at the way the wind is able to, expand or deform. That would be the word. It's deforming this liquid drop, whereas this liquid drop is not getting deformed. Again, that has to do with the surface. The surface is very strong here, so it has a very large surface tension. This one has a weaker surface tension, so it's more easily deformed. Okay. And then we've already looked at that one. Okay. Good. All right. So there's that type of problem. That one is the issue of surface tension, density, viscosity, which is resistance to flow, and then did I say surface? Oh, vapor pressure, which is evaporation. Okay, so it's like a fun little problem to do. Now, the one I want to spend the rest of the time on has to do with the nitty-gritty calculations of heat of vaporization. And so yesterday, what I did was I covered a topic where we went through, given the heat of vaporization of a liquid, we were able to find, the vapor pressure at a given temperature by using what we called the Clausius-Clayperon equation. Today, what we're going to do is we're going to look at the Clausius-Clayperon equation, and we're going to do a graphical analysis problem to be able to figure out the heat of vaporization of a liquid. So let me talk a little bit here. About this Clausius-Clayperon equation. Okay, so the idea here is that if you have a container of a liquid, so there's a liquid in this container, and it's at some temperature, I'll call that temperature T1. What will happen is there will be a certain vapor pressure above the liquid. So a certain amount of that material will exist in the gaseous phase. And so the liquid will have, well, I don't know if we say the liquid has it, but there is a vapor pressure above the liquid. Okay, so we'll call that P1. P1 for vapor pressure, okay? That pressure is a result of intermolecular forces and collisions and the escape of the liquid from itself. It has to overcome the surface tension, right? Which in the surface tension is a result of intermolecular forces, attractions. Okay. Let's make sure this is plugged in here. Oh, I'm sorry. Hold on one second. I have to take care of this. Let me plug this in. I didn't realize we were out of power. Okay. All right. Hold on one second. Let me go get something real quick. Okay, so the issue here is that if we increase the temperature of the liquid, that will result in more of the liquid transferring into the gas phase. So if we now increase the temperature, what will happen is so now we have T2. We'll have even more of that vapor above the liquid, right? So the pressure will increase. We'll have a higher pressure above that liquid. So this would be P2. So T2 is greater than T1, right? And P2 would be greater than P1, right? So that's the relationship. Now, it's not a linear relationship like it was with the ideal gas law. Remember, P equals nRT. So if you increase T, P increases linearly. The relationship's more complicated with Clausius-Clayperon relation. If you plot the temperature of the liquid on the x-axis and the vapor pressure on the y-axis, you get something that looks more like this. It's actually like an exponential curve, okay? And what we said was that once we reach atmospheric pressure, 1 atm or 760 torr, this would be the boiling point, right? The boiling point is the temperature at which the vapor pressure above the liquid is equal to the external pressure, the pressure of the atmosphere. So the boiling point is the temperature at which the vapor pressure is equal to the external pressure. And the external pressure is the atmospheric pressure. This is why liquids will boil, like water, will boil at lower temperatures at high altitudes than they do at low altitudes. Okay. So if the atmospheric pressure is here, so imagine you're at high altitude, there's a lower atmospheric pressure, right? So that will occur here, right? So your boiling point would be at a lower temperature. I'll call it a low boiling point because the atmospheric pressure is lower. That curve, which is measured experimentally, it can be calculated, but generally it's measured. People will make, 100 measurements along these curves to figure out what the curve looks like. That curve determines whether something is a solid, a liquid, or a gas. In this case, we're looking at the gas and liquid phase, the difference between gases and liquids, okay? So that's the equation that describes this curve. That is called the Clausius-Claperon equation. It is an equation that we use to calculate these curves. Now, again, in practice, we don't calculate them. In practice, we measure them because each liquid has its own eccentricities, its own, little minor details. But if we make measurements, we can then do calculations using the Clausius-Claperon equation, okay? So what I'm gonna do is let me come up here. I'm going to actually write down the relationship here. Let me look on it in terms of an image. There we go. Okay, now the Clausius-Claperon equation, the version that we saw yesterday was ln P2 over P1, right? So those are the vapor pressures, is equal to minus delta H over R where delta H vaporization is the heat of vaporization, the amount of energy required to boil a mole of that liquid, times 1 over T2 minus 1 over T1. Now, it's not uncommon for people to have this be a positive here. But if that's a positive there, then it's 1 over T1 minus 1 over T2. It's just whichever version of that you want to have, okay? Now, what I'm going to do is I'm going to show you another form of it, which is P2 is equal to P1 times E to the delta H over R. times 1 over T1 minus 1 over T2. This is another form of it. Okay. This is another form of the equation right here. This one doesn't have the natural log in it. It has the exponential. But remember, the natural log and the exponential are inverse functions of each other. So essentially what happens is if you take if you take the first form of this, the one that we did yesterday, and you say E raised to both sides, you can manipulate it and get this form right here. Again, you know, the reason this is not negative here is because they switched the T1 and the T2. Okay, so whatever, that's just an issue there. Okay, so what I want to do now is I want to look at a particular problem, and I'm going to show you a form of analysis that we can do using, you know, this form. Okay, we're going to use a modification of this form in order to do an analysis. The goal here is we're going to want to use data. So let me write that down. We're going to use pressure and temperature data. That's what we're measuring to calculate delta H vaporization. Okay, and this is a kind of analysis that's very common in the physical sciences, where we measure data, we measure a mathematical relation, a physical relation, pressure and temperature in this case, and we use a graphical analysis to figure out a particular, what's called a parameter, a quantity. In this case, it's delta H of vaporization. So we're going to use PT data to calculate delta H vaporization using a form of this equation right here. Okay. And so essentially, let me take advantage of a particular relation. So this is a relation involving logarithms. Okay, and that is that if you have the natural log of a ratio, I showed this yesterday, the natural log of a ratio is equal to the difference in the natural logs of those two quantities. All right, so ln of A over B is equal to ln of A minus ln of B. Now there's a related relation, which I'm not going to use right now, but we should be aware of it. The natural, or the log, this goes for any log, including the natural log, the log of the product of two quantities is equal to the sum of the logs. Okay, you add them. It's kind of cool, right? That's just one of the properties of the logs. So if you multiply the two together, you get the sum. If you divide, you get the difference. Okay, nothing magical about it. It's just the way the log functions are defined. Okay, so what I'm going to do with this version up here is I'm going to take advantage of that, and I'm going to write it as ln of P2 minus ln of P1. And that's going to equal minus delta H vaporization over R times 1 over T2 minus 1 over T1. And then I'm just going to go ahead and add ln of P1 to both sides. Right, this is minus, so I'm going to add it to both sides. Okay, and now what that's going to do is it's going to give me a relationship that I can use. So I'm going to come over here and bring up this problem. And let me show this too. Okay. So it says here, the vapor pressure of substance X is measured at several temperatures. The goal of this is we're going to calculate the enthalpy of vaporization from the vapor pressure. Okay. So it says here that if the temperature is 0 degrees Celsius, the vapor pressure is 0.119 atmospheres. If the temperature is 12 degrees C, the vapor pressure is 0.153 atmospheres. And if the temperature is 24 degrees C, the vapor pressure is 0.191 atmospheres. So there's 3 temperatures and there are 3 vapor pressures. And we're asked to find the enthalpy of vaporization of this liquid. Now, I want to point out that 3 measurements is a very small number of measurements. In practice, if we really wanted to do a good job on this experiment, we would do 6 or 7 at a minimum, because the more data that we have to collect, the better our statistics will become. So this is really just a problem designed to kind of teach you how to do this form of analysis. It's not really a real problem in a sense, because again, unless it was like a really unusual material that experimentally was very hard to make the measurements, we would never do this with 3 measurements. That would just be rejected by most scientists as invalid. We would want at least 5 or 6 or 10 more measurements there. 3 is a pretty much the minimum of what you can do. Okay, so there's a relationship between temperature and vapor pressure. And what I'm going to do, stop share, I'll put that data up here, is I'll recreate this table. So I'm going to put the temperature in degrees C. And so we have 0, 12, and 24. And then we have the vapor pressure, which is in atmospheres. That's fine. And this would be 0.119, 0.153, and 0.191. Okay. Now I'm going to make another 2 columns. The first column, I'm going to switch. Actually, I'm going to do more than 2 more columns. I'll do 3. I'm going to switch the temperature to Kelvin. When we're dealing with pressures of gases, we generally want to have the temperature being gas in Kelvin. So I'm going to add 273. Okay, I'm just adding 273 to the degrees Celsius. So this would be 297. Okay, so now we have our temperatures. The next thing I'm going to do, I'll make a little dash here, is I'm going to take the natural log of the the natural log of the pressure, ln of P. Okay, and I'm going to describe why I'm doing that in a moment, but let's just go through it. So what you do is you take your calculator and you either hit the ln and then 273 equals, or if you're using one of the TI-30s, then you do the opposite. You put in the number 273, oops, sorry, 0.119, because we're doing ln of pressure, 0.119 and then ln. So 0.119 ln, and you get negative 2.13. Then you do ln of 0.153. And you get negative 1.877. And then you take ln of 0.191. And you get negative 1.655. Okay. I guess, I went 3 digits for the second and the third one. So let me do 0.119 again. Negative 2.129. Let me do it that way. There we go. Okay, so there's ln of P. And I'm going to do one more column, which is 1 over temperature. And this is in reciprocal kelvins. Okay, so right now, I'm just going through the calculations here, and then I'll talk a little bit more about why I'm doing it this way. So now I'm just going to take 1 over 273, and you get 0.00366. Okay. 285, reciprocal, 0.00351. 0.191, reciprocal. Oops. I did it. I'm sorry. I keep going back and forth between P and T. We're doing 1 over T. So 297, 0.00337. Okay. So I've done those two. Now let me see if I can. I want to bring this up for you. Let me see if I can get this open. There we go. There we go. Okay, so I'm gonna, oh man, let me save this. I don't want to stop share. Okay. Now I'm going to come back to the Clausius-Clayperon equation. Okay. So P equals P0 e to the minus e sub a. I'm sorry, not e sub a. Delta H over RT. Okay, so this is a simplified form of the equation. And essentially what I'm going to claim is that if you take the natural log of both sides, you get ln of P is equal to ln of P naught minus delta H vaporization over RT. Okay. And so this form of the Clausius-Clayperon equation, all I did was I took the natural log of both sides. So when I took the natural log of P on the left side, I took the natural log of the right side, and I took advantage of the idea that ln of A times B is ln of A plus ln of B. So ln of P times e to the minus delta H is ln of P naught. This is what we might consider the initial pressure. P naught. Now here's our heat of vaporization. This is what we're trying to find. Okay. Now here's what I'm going to do. I'm going to do a graphical analysis. A graphical analysis, we're going to use linear regression. This is a technique you use in Chem 12 quite a bit, so it's good that we're going over it right now if you have time to look at this. The idea of linear regression is that a line can be described by a relatively simple mathematical equation. The idea is that if you plot y on the vertical axis and x on the horizontal axis, you will get something that looks like a straight line. Okay. And that line has two parameters. One is called the slope, and the other one is called the y-intercept. Okay. Now, the slope is equal to the change in y over the change in x. From a practical perspective, it measures the steepness of the line. So the steeper the line is, the larger the slope is. So for example, this line right here is very steep. So this one has a large slope. This one has a smaller slope. If it's horizontal, the slope is 0. Okay, so large slope, smaller slope, no slope at all. But you can also have negative slopes. So a negative slope would look something like this. Here's one like that. This would be a negative slope. And it turns out that if we do use the Clausius-Claperon equation, we'll end up with a negative slope. And I'll explain to you how that works in a moment. Now, in practice, let me erase all of this. Let me get rid of this part here. What we do with this equation is we graph ln of p on the y-axis and 1 over t on the x-axis. So that's why I did those calculations. This right here is going to be our y. Those are the values of y. And these are the values of x. Okay. So the graph, I'll just show you real quickly here. The graph is ln of p on the y-axis and then 1 over t on the x-axis. And in general, what you get is you get a negative slope. And I'll show you with these 3 points that we get a negative slope. Okay, so there's a line that we can connect those dots with, one straight line. And the slope of that line is equal to minus delta H vaporization over R. The slope is equal to that value. Now remember, R is a constant, 8.314 joules per kmol. So if we know the value of R and we measure the slope, we estimate the slope from the graph, we can calculate delta H of vaporization. And this is a very standard problem in Chem 11, but also in Chem 12, when you do what's called kinetic analysis. You'll do these kinds of graphs here. So here's the idea then. Step 1, we calculate ln of p. Step 2, we calculate 1 over t in Kelvin. Make sure it's in Kelvin. Step 3, we plot the points with y being ln of p and x being 1 over t. Okay. Step 4, we estimate or calculate the slope graphically. And then step 5, the slope is equal to minus delta H vaporization over R. So that means, that implies that delta H vaporization is equal to minus R times the slope, right? So we graphically estimate this slope. Then we plug that in, multiply it by minus R, and that gives us delta H of vaporization. Okay, that's the procedure. It's essentially 5 steps to be able to do this problem. So we've already done the first 2, right? We've already done the ln of p calculations. So that's over here, and I put y above it. And we've already done the 1 over t in Kelvin. So that's the x there. So we're really now, we're just ready for step 3, which is to plot those points on a graph, estimate the slope, and then just plug it in to figure out delta H of vaporization. Now, there's another thing you can do. You can actually figure out the boiling point of the liquid, because you remember, if something is boiling, as long as you're in atmospheric pressure, the boiling point's at 1 atmosphere. Something will boil when the vapor pressure is equal to 1 atmosphere. So you can also figure that out from this calculation. Okay. So let's go through this. I'm going to do the graph now. So like I said, I've done step 1, I've done step 2, but now we're going to do step 3, which for most people, step 3 and 4 is the hardest part. 1 and 2 is usually pretty easy. All you got to do is use your calculator. 3 and 4 is harder. Okay, I'll erase 1 and 2 because we already did those. And that'll give me a little more room for the graph. Okay, so it's going to be a linear graph. So I'm going to try to draw this as best I can. We only have 3 points to plot, so that's pretty cool. If you go on to take Chem 12, you'll do graphs where you got to do 5 or 6 points, but that's fine. Yeah, that's not too bad. Okay, so this is the x-axis, right? So this is 1 over T. And remember, the units are reciprocal Kelvin because you're taking 1 over the temperature, right? And it will not, you will not get the right answer if this is in Celsius. So make sure you got in Kelvin. And then on the y-axis, we're going to have ln of P. Okay. Now, one of the things that's kind of challenging here is to go about figuring out what the numbers are here. So here, this is -2. So I'm looking at the y-axis now. One of the values is -2.129, and the lowest value, I'm sorry, the third value, not the lowest, it's actually the highest value, is -1.6. So I have to then create like a range on this graph, and sometimes that's a little challenging. So I'm just going to go up to here, and I'm going to make even divisions. Let me erase that last one up there. There we go. Okay, so I want to make even divisions. Those are not exactly very even. Let me, graph paper is better. So we'll start right there. I'll go even divisions like this. There we go. And I just want to make sure that all 3 of those points fit on this range. So I'm going to make this one -1 point. Let's do it smaller. I'm going to make this -2.5, -2.3, -2.1, -1.9, -1.7, -1.5, -1.3. There, that's pretty good. So what I've done is I've ensured, by doing that range, I've ensured that all 3 of these values are going to fit inside here, right? You don't want to do it so that these numbers, that -2.1 is all the way down here. You want it to be in that range there. I'm also trying to use the convention that most people will use, which is the more negative value is at the bottom and the more positive value or less negative values at the top. You don't have to do it that way. You could do it the reverse, but it can lead to some confusion if you do. So, we're headed towards 0, right? These are all negative values, but we're going up towards 0. Okay. Now I got to do the same thing over here. Now, these over here, you can do a nice little thing, which is put them in scientific notation. So I'm just going to move this over 3 places. 1, 2, 3. See, all of them are 3 places. So 3.66 times 10 to the minus 3, 3.51 times 10 to the minus 3, and then 3.37 times 10 to the minus 3. I find it easier to put them in scientific notation if the values are so small. Let me move this out of the way. Okay, so now we want to go from -3.37 all the way up to I'm sorry, not -3. I want to go from 3.37 all the way up to 3.66. So what I'm going to do is I'll put 3.0, 3.2. Well, let's make them a little wider. I'm sorry. 3.1, 3.2, 3.3, 3.4, 3.5, 3.6, 3.7, 3.8. Let's do it like that. Okay, so these are all times 10 to the minus 3, and that will be important when you try to calculate the slope. So make sure you got that in there, okay? So now we just plot the points. Again, all these values here will fit in that domain, okay? And they're evenly spaced, so you can't, don't do, 3.0 is here, 3.1 is right next to it, and then 3.2 is over here, right? You want them evenly spaced. This is a linear graph. 3 points. So the first point is negative 2.129. One of the problems you may have with these problems is that you may have learned how to do arithmetic in a math class where all the numbers are usually very nice. 3x squared, 13y to the third. Here you're going to have, negative 4.172, those kinds of numbers. So negative 2.129 would be about right there. And that corresponds to 3.66. So 3.66 is all the way over there. So you got to kind of connect it to 3.66, which is about right there. So there's 1 point right there. The second point is negative 1.877. So that's almost negative 1.9. It's about right there. And that corresponds to 3.51. So 3.51 is right there. Third point, negative 1.655. So that's negative 1.6 would be right there. 655 would be halfway down from there. So negative 1.655, and that corresponds to 3.37. Okay, so there's our 3 points. Now, I guess you could criticize me for the way I pick the range on the x-axis, the domain on the x-axis. I probably should have started at 3.2 and gone up to 3.8. That might have been a little bit better, but that's okay. It still works. So now I'm going to draw a line. Now, again, they're going to give you data that works out very nicely. So there's our straight line. Okay. Now, what I'm going to do is I'm going to estimate the slope. So I just did step 3, negative slope, right? Positive slope, negative slope, zero slope, infinite slope, right? Okay. So now what I'm going to do is I'm going to estimate the slope. That's step 4. Delta y over delta x. Okay. So here's how I'm going to do it. I'm going to take this point right here, 3.2. Let me use a different color for this one just so you can see it. I am picking 2 points that go a little bit beyond the points that were in the measurement, just a little bit beyond, okay? And I'm going to use those 2 points to estimate the slope, okay? So we wouldn't want to do it this way. We wouldn't want to pick this one and this one. You could estimate the slope that way, but it's not a very good way to do it. And we wouldn't want to do it, say, like from here to here. We want to pick points that are a little bit beyond all of the points in the measurement. It will give us a better estimate of the slope. Okay, so how do we figure out this delta y over delta x, which is the slope? Okay, so since we're using the red one, let me put this in red. Okay, well, delta y, let's figure out what delta y is. Delta y is essentially the height of this triangle that I'm drawing, right? In red, I'm drawing a triangle. It's a right triangle with the hypotenuse being the actual line itself, okay? So the slope is actually equal to the height of this triangle divided by the base, okay? The height over the base. Okay. So now, how do we figure out the height? Well, you just figure out how tall that is. It starts off right here. So that's about negative 2.4. and it goes all the way up to here, which is negative 1.3. Okay, so negative 1.3 minus a negative 2.4. There's your delta y. Okay, negative 2.4, negative 1.3. Okay, now we're going to do the delta x, the base. So the base goes from 3.2 to 3.8. So 3.8 times 10 to the minus 3 minus 3.2 times 10 to the minus 3. Okay. Don't forget that 10 to the minus 3. That 10 to the minus 3 is important. It's a factor of 1,000. So now, if you take negative 1.3 minus a minus negative 2.14, you get 1.1, right? Because you're adding the 2.4. And then if you take this difference, you get 0.6 times 10 to the minus 3. Okay, now look at the slope. This is a negative slope. So this is negative. Okay, so remember that negative, this is a positive slope. This is a negative slope. So it's got to be a negative slope. Let me erase the equal sign and put that in there. Now, 1.1 divided by 0.6 is 1.83 times 10 to the 3. Okay, why did I get 10 to the 3? Because if you take 1 over 10 to the minus 3, you get 10 to the plus 3. Okay, so there is your slope. You got your slope now. Now, it turns out the slope is in Kelvin. The units are Kelvin because ln of p doesn't have any units. So you do the same thing with the units that you do with the numbers. So if your slope is y over x, delta y over delta x, then if something has no units, we just write a 1, and then over delta x. So these are the unit analysis. No units on the y-axis, but the x-axis is 1 over Kelvin. So 1 over Kelvin is just Kelvin. So your slope has units of Kelvin. Okay, so we've estimated the slope. Graphically, the last step is to figure out what delta H vaporization is, and that is simply minus R times our slope. So let's get rid of this part here. So step 5, delta H of vaporization is equal to minus R times the slope, which is minus 8.314 joules per kmol, times minus, I forgot the minus there, minus 1.83 times 10 to the 3 Kelvin. Okay, minus R times the slope. Remember, the slope is negative. So what happens when you multiply a negative times a negative? You get a positive, right? So if you multiply 8.314 times 1.83 times 10 to the 3, you get 15,200. The kelvins cancel and you're left with joules per mole. Okay, it should be positive. Heat of vaporizations are generally positive. That would be correct. It's just that typically when we're in thousands of joules, we convert it to kilojoules. So divide by 1,000 and you get 15.2 kilojoules per mole. So there's your heat of vaporization. For perspective, the heat of vaporization of water is 44 kilojoules per mole. So this is quite a bit smaller than that of water. Boils at a much lower temperature. Okay, so we've now figured out the heat of vaporization by using the Clausius-Clayperon equation. Okay, so there's, again, two forms. ln of P2 over P1 equals minus delta H vaporization over R times 1 over T2 minus 1 over T1. This is the type, the form of the equation. You use this form when you're given 3 out of the 4 PT values. Okay, or all 4 and asked for delta H. So for example, they'll say P1 equals, P2 equals, T1 equals, and then ask you for T2. Or they'll give you all of them, P1, P2, T1, T2, and they ask you for delta H. Okay, if you're given a set of data where you're given P and you're given T and you've got at least 3 values, then you're going to use this form, which is the ln of P equals minus delta H vaporization over R times 1 over T plus ln of P1 or P0, I think I called it. Okay, and then this is going to be Y, this is going to be X, and then this is going to be the slope. So I gave you one form yesterday. That's what you do if you're, given 3 values and asked for the 4th, or given all 4 and asked for delta H. But if you're given a set of data where you have at least 3 values of pressure and 3 values of temperature, then you use the graphical analysis and that form of the equation. This is superior. This is the better form than this one, because this one has only got 2 values, 2 pressures or 2 temperatures, so forth and so on. When you have 3 or 4 or 5 or 6, you're going to get better results out of that. So as I said at the beginning, scientists, when they measure delta H of vaporization, they're going to do this form. They're not going to do this one. But this one is used for some reason in chemistry textbooks. It's on Alex. It's in all these books. You'll see a very similar form to this in Chem 12 when you do chapter 13, which is called chemical kinetics. And there's an equation that looks a lot like these, and you'll do a similar analysis with those. Okay. So that is the last one of chapter 11 that's on the assignment. So I'm going to end it right there. And good luck with everything. I hope you have a chance to do some of this as extra credit. It might help you a little bit in Chem 12 when you take that. But good luck with everything.
Thank you. I missed the part where we, why did we change to a negative R value? Is that just so that we get a positive, because we had a negative slope, so that we end up with a positive heat of vaporization value?
So what's found is when you see these forms of equations, very commonly, what happens is oh, I should put that in the same form. Let's do it this way. Very commonly, there's a negative in here. Okay, it pops up a lot in these forms of equations, because essentially what happens is, if this is positive, then what would happen is, as you increase temperature, what you would get is
it becomes smaller on top.
It would get smaller. It would just get smaller, right?
Right.
So by this being negative, it gets larger, right? So in practice, I mean, look, in practice, what we do is we saw this with chapter 6 when we were talking about like electromagnetic waves and all that. People were trying to fit those line spectra. You essentially, what people will do is they'll say, well, let's just come up with an equation that seems to fit the data. Einstein did this too, and see if it works. And so what you end up with is, very commonly, this has to be a negative. And so the result of that is, when you do the arithmetic, you take the natural log of both sides, right? Because whatever you do on the left side, you got to do on the other side too, to maintain the equation. Then what you get is, okay, ln P naught, but that negative there shows up here. Oh, I keep putting EA because I'm used to doing this in general Chem 2. Right, so that negative there, it comes down here. So now when you do the graph, we're not putting the negative in the graph. We're just doing ln of p versus 1 over t. We're not doing negative 1 over t. We're not doing negative ln p. So you get a negative slope. Right? And that's just the nature of the graph, is you're going to get a negative slope. But based on the way we're graphing this, this is x, right? The 1 over t is x. So the slope is this. Oops, sorry. The slope is this. It's the negative delta H over R.
Mm-hmm.
So in a sense, there's two negatives, right? You got the negative from the equation, but you also have the negative because the slope
actually negative.
is actually negative. So then, when you have this form right here, if you're trying to find, without the negative, right? We're just trying to find out what that is. We multiply both sides by R, but that gives us negative delta H vaporization, right?
So
We don't
we
want negative delta H, we want positive delta H, right?
Right.
It'd be like if I said, y equals 3x minus 2, and I said negative x equals 4, you don't want negative
like, what's x? Right.
Not that that's the actual solution to that, but so you multiply both sides. So now you have negative R times the slope.
Okay.
Now, in practice, what someone would do is they would just say, oh, just give me the magnitude of the slope. The slope is 1,000 or 2,000 or 3,000. I know it's negative. So now I know I just got to take 8.314, and then just multiply by that, whatever that slope is, whether it's positive or negative, and not even worry about the negative, because I can see this is negative, and I know the equation tells me that if the slope is negative, the value will be positive, right? That's in practice what people do. So like if you did the data and you came up with this, you would know something's wrong. The form of the equation that fits this should be, like that.
With a negative slope, right?
And that'll give you a positive value for.
And you're just taking kind of the absolute value of the absolute value to get the.
That's right. You're just taking you're just trying to make it positive, really. And the logic behind that is that it should take energy to boil something, right? Delta H of vaporization is the amount of energy or enthalpy required to boil a mole of a liquid.
Right. So it doesn't make sense that it's negative, because that means.
Yeah, I mean, that would be amazing. That'd be a magic material, right? If you had a material that actually gave you energy when you boil it, they'd be using that, right? That would be very useful. But it doesn't work that way. We don't get something for now. You don't get energy out of, you doing the work. You don't get energy out of that, right?
Okay.
When something does the work, you get the energy, right? So it doesn't work that way. Okay.
Got it.
Yeah.
Okay.
Awesome.
Thank you.
All righty. Take care.
Bye. Have a good day.